All right.
There we go.
I'm not here because I flew in from my hair early this morning and I need some home time.
Understandable. Ah, they're good, Steve. Glad to have you. All right.
Alrighty.
See your screen now.
Oh, now we're good. All right. Yeah. So this is just my tales of the trenches, about 20 years of data center design, construction, operations, and a little bit of pain. So we'll share some of those lessons. Um, yeah. So so this is a disclaimer that these are my opinions and mine alone. Um, but I will share uh, everything I can. Um, so just a little bit about me. I'm currently the lead of National Lab of the Rockies Advanced Computing Operations Group. Main area of expertise is in data center design. I've joked that I've had every job in HPC except for a network engineer, and you do not want me touching your network. But I've done a lot of other things. Primary leadership roles at National Renewable Energy Lab, which is the previous name of National Lab of the Rockies, and then the National Center for Atmospheric Research. I'd say a lot of my career has been about pushing boundaries of energy efficient computing, and that's kind of all the way from the algorithms, software stack, data centers, rack level cooling, um, all the way out to the cooling plant. So, um, as I mentioned, I've been at this like feels like a long time, 30 years. Started out as help desk kind of person, and I never left. I also never feel like I had the same job for more than about 6 months at a stretch, although I was the lead design engineer for um, the NCAR facility, and that was almost a decade of those 20 years. So I'll tell a little bit about that. Um, yeah, so why does this stuff matter, or why am I passionate about it? We don't have to pick up too many newspapers or any trade magazines that we're at 2% of energy use in data centers currently, and that is rapidly increasing. Um, Done poorly, it's often worse than 40% of data center energy use goes to just the cooling. And if you pay attention to a number of the design aspects, you can save both a lot of money and a lot of resources. And those two things certainly get me excited. So, um, I've worked at some really terrible locations. Um, so the upper left is the NCAR Mesa Lab. If you've ever been to Boulder, it's it really does look like that, and it sits right at the foothills of the Flatirons. And kind of interesting anecdote at the Mesa Lab. That building was built in 1965. It actually had a data center purpose built in it. So I think it was one of the earliest I'm aware of. Um, and originally was designed for CDC machines. Um, it was expanded in 1975 to house the first Cray systems. NCAR took delivery of a Cray 1 serial number 3 in like 1976. Um, and just for the record, I was not there at that time. Um, but I did inherit that data center in like 1996. At that point, it was pretty long in the tooth and had a number of operational issues that I didn't quite run away screaming, but I thought about it. So, um, the upper right is the NCAR Wyoming Supercomputing Center. That's where I spent a better part of a decade justifying getting that funded, and in the design and engineering of that facility. And kind of interestingly along the way, this is the ESIF facility in the lower right, and that is the facility that I currently operate. The center part of that is the data center. The prominent part that's kind of sticking out on the cantilever there is the office building, and then the space to the north is high bay space where they do all kinds of fun experimental electrical things with like faults and high voltage DC and other things that are kind of interesting to have on the same building for your electrical. They are completely independent, and by design, that is key because the faults don't travel into the data center. Um, but I'll talk a little more about that. And on the very north side, there's a electrolysis machine and hydrogen also. So it's an interesting data center from a risk perspective. So I think I'll pause there if there are just any quick questions.
One question that I have is, what's probably the biggest challenge of building out west of the Rockies comparatively to, say, Ashburn area?
Oh, all construction problems are local, and it's your permitting is, I don't know if it's different, I think, but I would say you got to know exactly what your local code requirements are, your AHJs. There's nuances and various things. And I can definitely highlight a couple things that we learned at Wyoming. Like one of the things up there is it's not an active uh, earthquake zone, but you are relatively close to Yellowstone. And the AHJ at that point had just attended a class on um, earthquake and large raised, supported ceilings. And so he made us change all kinds of design aspects of that because I think primarily he attended that class and was like, well, if Yellowstone ever goes off, we have bigger problems. But yeah, so those are probably one of the, um, certainly in the southeast, like we're able to take advantage in both of these facilities of direct evaporative cooling, and it's massively efficient, and it's how we're able to get some really stellar numbers. I'll highlight at the very end of my talk kind of where we're headed for the broader industry, and I think there's some hope there that makes design easier and a little more less location dependent. So we can talk about that too.
Could you define a term for me?
Sure.
HJ.
Oh, authority having jurisdiction, AHJ.
AHJ. Okay, that makes sense. Thank you.
Yeah.
So are those signs actually that is beautiful? Or is
Yes.
that just for the stadium?
It's not always that green, but yeah,
Because that looks like that's just beautiful.
yeah. And I will. So the first place, the Mesa Lab, the computing division at that time, yeah, it's a gorgeous location, but they put us all in the first basement. So we had no views. But you could walk out at lunch and it didn't suck. Let's put it that way. The Wyoming site is west of Cheyenne, so it's a different kind of pretty. You certainly don't have the Rocky Mountains, and then the third facility is really built into South Table Mountain, and it does look like that. So,
Aaron, I got a question for you. And I'm not familiar with these locations, but I would imagine that the availability of water could be a challenge or enough water. Is that part of the reason you focused on efficiency?
It's an interesting question, and actually, we made design choices that prioritized efficiency electrically, and they actually do have some impact on water.
Right.
Um,
That because electricity is so expensive there.
it's the biggest cost. So, like, if you looked at first order terms and second order terms, the cost of water was uh, on the order of $20,000 a year. Whereas the electrical costs for the kind of sizes we were at, you know, were $1 million a year on the electrical.
Holy cow.
Slight difference.
So so we prioritized more on our total cost, and that did impact water usage to a degree. Um, Water is a big deal in the West, so it like I say, I'll highlight a few things thinking about. So let me move it along here. Um, so I've had the pleasure of working with a whole bunch of really boring technology. Um, the the first four systems that I have pictures of were actually at the Mesa Lab location. So the first major liquid cooled system I was involved in the planning and installation of is a Cray C90 in the upper left. Um, we then had a Cray 3 system, which is the one in the lower left. Um, Probably a career highlight there. I actually did get to meet Seymour Cray when that system was on the floor. And, as a young mechanical engineer, I was like, that's a celebrity, um, which was pretty cool. For a long time on a single CPU performance, that was the fastest system we'd ever tested. Um, Very interesting. Fully immersion cooled, used a immersion cooling called fluorinert, which is also a PFAS chemical, so not the greatest thing. It was originally an artificial blood plasma. So that vat of liquid is actually, flowing water through it. The lower half of that is or this fluorinert liquid. Lower half of that is all pumps and plumbing. So the actual CPU is equivalent of four cores, not quite the same thing because they were vector processors, they were gallium arsenide, everything in them was gold, and they were a vector CPU. So totally different creature. Um, but that's where the industry completely flipped. And so the next system on the upper right is an SGI Origin. Um, I thought I was big time hotshot when I had it going across to 128 CPUs for a CFD application. For the time, that was pretty impressive. Now you've got 128 cores on a single socket. So, but at the time, that was pretty cool. The slanted machine is not leaning on purpose, or it is on purpose. It's actually a Blue Gene L, if you're familiar with that system. So those were very stripped down, massively parallel systems, and it's actually an air vent system. So the front half of that is a scoop, and the back half is the exhaust. So you could nest those things together, kind of like a Rubik's snake, if that makes sense. Um, Argonne at the time had a very big Blue Gene L system. So if you go to the middle, the first system is a Cheyenne system. So that was an IBM RS6000 architecture. That was an air-cooled system with rear doors because that was the first time we saw racks that were in the order of 40 kW. Um, next system is the return of liquid cooling for NCAR. So that is a SGI architecture that was purchased right before we took delivery by Hewlett Packard Enterprise. And it just so happened to be the same architecture as the Eagle system in the right. So those were SGI architecture, HPE delivered systems. And then the lower right is our current HPC system, which is 100% direct liquid cooled. And that system is 256 kilowatts in a cabinet. So I have a single row that is 2 megawatts um, in the data center. So, um, like I say, lots of boring systems. It's been fun.
Aaron, for the
Um,
Castrol,
go ahead.
are those red and blue hoses part of the water cooling?
Yes, they are. So, yep, as you would expect, cool or blue is the cold water supply to the node, and red is the um, hot water discharge coming off.
Wow, that's neat. Is it set up with like individual blades? Each one has its own cooling.
Yes. So each one of those, like you can kind of see the handles and the locks with the quick disconnects there. Um, that is 4 nodes per tray. So it's eight CPUs in a single tray. Um, and everything in that node is liquid cooled. So CPU, memory, network, power supplies. Um, the actual CPU is a cold plate that's like physically, thermally um, touching the chip. A lot of the other components are cold plates that, just flow nearby whatever the heat source is and capture the heat. Um, but yeah, that is 100% liquid cooled system at that stage. Same architecture as um, Frontier at Oak Ridge, El Capitan at Livermore, and it's the Cray EX product line. So that was a Cray design, also bought by Hewlett Packard Enterprise. So there's stories there, but I won't go into those.
Wow.
Thank you. Were your power supplies good the first time around?
Yes, but we were like shipment 4 or 5. Some of the early ones I don't think were as lucky. So jump into a little bit more of my history and kind of how I got where I got in certain regard. In 2003, had a fateful cup of coffee in the cafeteria at the Mesa Lab, and we um, were discussing that every amount of electrical or cooling infrastructure that we installed in that facility immediately got gobbled up by the system. We were only capable of about 2 megawatts at that site. Um, and we could see, forecasts of where we thought chips were headed, and we're like, we're in big trouble. Um, so that cup of coffee became a justification on why we needed to build a new building. That took many twists and turns. We knew it was a big enough project that we probably shouldn't take that on alone. And we started shopping the idea with a number of the universities and other potential partners. Several site locations. I don't think Wyoming was in anybody's radar in 2003. One thing led to another, and we ended up there. Um, so I, you know, led that effort and the design phase. We, fateful cup of coffee in 2003. We finally got a green light 2005. I got recycled at least 4 times through different leadership changes over about 3 years, and we finally got the green light to design and build uh, late 2007. And we started construction in summer of 2008, and we were online in 18 months, which for the time seemed like crazy fast. The AI companies are now doing it in like 3 and 4 months, um, which is even crazier. But that project came in. We were 2 million under budget and 4 months ahead of schedule. So everything went pretty well because we had at least 5 years to think about it.
Wow.
Um, Similar time frame. The ESIF facility was in at least kind of concept design, and kind of an interesting interplay, and why I'm at National Lab of the Rockies now. In part was I was design engineer for Wyoming, and ESIF was in the just slightly behind NCAR's planning. And so I ended up on an advisory team for ESIF. So probably not coincidentally, the two facilities have a lot in common. And we had a number of engineering firms that were in common between us both. Um, I alluded to that we're looking forward to kind of what's next, and that's a current effort at the lab that we're engaged in, which is part of the COOLERCHIPS program. And obviously still leading the advanced computing operations team. And we, believe it or not, we're finishing up the last upgrade that we can in the ESIF data center. Our next system will be easily housed within that facility, but I'm starting to think about what's the next facility we need. So I may get to do this like at the front end of my career and the back end of my career. So we'll see. So I'll jump into the NCAR facility. This is the aerial overview. 150,000 square feet, designed, highly modular components internal. But a kind of unique aspect of this build was you get about one building out of a Washington, D.C. approval every 20 years. So we built a core and shell that was sufficient, we thought, to last 20 years. The internal components, I had no idea what technology would look like 5 years later. So we just made it big, square, and boring. Um, and lots of space to be able to move components in and out. So internally, a lot of components are modular. We did let the architects go a little nuts. And so you've got the large, like round rotunda for the building. That's the main entrance. And you know, I had all kinds of humorous interactions with architects, but they wanted to make it look like a high-tech building, and they were all enamored with printed circuit boards, and so that drum is basically a capacitor, and all the square blocks are like components that you would see on a motherboard.
Shocking decision.
Yeah.
I think it might have insufficient glass.
So, uh, so yeah, that's the exterior of the building. I'd say one of the things that was hugely beneficial, some of the players that we were able to engage, and I already alluded to, I was on the advisory team for NREL at the time. I had a counterpart at NREL that was on my advisory team, and that was hugely helpful. The big three design firms for this project was California Data Center Design Group. They've changed their name, but they still have the same logo. Rumsey Engineers, they're out of Peter Rumsey, I think is now a professor at Stanford, but very interesting guy. Was really kind of the concept guy for both facilities, the NREL and the NCAR one. And then RMH Group was a local local group. I also got a ton of advice from they were the original founders of Uptime Institute. They've also long since retired, but they gave me some really good advice that I ignored, and um, they advised that, plan to get a big project like this recycled at least twice. And I was, young and confident, and that wasn't going to happen to me. So I got recycled 4 times. Um, and then, the key thing that I learned after getting recycled the 2 times is you had to develop multiple executive level champions because they change on you. We had like 3 presidents change. We had like, well, not three. So let me go from top to bottom. We had 2 US presidents change. So we started the idea under the Obama administration, and then we um, shifted to the Bush administration. That nearly killed the deal, except for the governor of Wyoming sat down with Dick Cheney and got it off of life support and back on. Um, there were a number of twists and turns. NCAR changed directors 3 times, and it was very key to develop multiple champions. So, and yeah, uh, take the opportunity anytime you get recycled to rethink your ideas and make them better. So,
Aaron, I have a question.
sure.
I don't totally understand what you mean by being recycled. I thought you were making a crack about the hardware at first. Are you talking about like the project getting scrapped and having to bring it back online?
Yes. So I'm thinking more of being politically recycled.
Aha.
Um,
Okay, thank you.
that we would justify the project, we would be very close to getting approval to put shovels in the ground, and then something would happen and we'd have to go back and start over. So very painful experience for an engineer who's like, this is a brilliant idea. I don't understand why you can't get this. Um, but you had to almost start over every time you had a major leadership change. So more of a political thing than a technical thing for sure. So for NWSC, a couple things that we did that were relatively unique. You have to recognize that at the time we were sitting there, we'd had liquid cooled machines, we'd gone to air cooled. We could see the trend, but we couldn't quite figure out if we were too early on the trend, but we committed to liquid cooling for our larger systems. And that drove us to the decision to go to these evaporative cooling towers that I mentioned. And at NCAR, I wasn't quite brave enough. We had the funding to put in a chiller, and so I did. And we can trim like 4 or 5% of the year if we're too hot, um, based on outside conditions. In reality, we hit those conditions at 3 o'clock in the afternoon after a thunderstorm rolls through in Wyoming, and it's 102 out. So it only happens about 4 to 6 hours a month in August and September. So if I had to do it over again, I wouldn't have put the chiller in. But lesson learned there. At the time, we needed to have the capability to go colder, in case the technology didn't go the directions we thought it would.
If you didn't put the chiller in, how would you provide the cooling even for that 4% of the time?
You climb, but you don't climb out of any kind of safe zone.
Okay. So you're just using the data center as a heat sink.
Correct. If you got enough capacity, and I'll highlight it in the ESIF facility, but they did not put a chiller in. So we just get a little warm in August and September and are able to ride through. So that facility also, we went to a low energy fan wall design. And in all cases, we oversized piping, we oversized plumbing, and the fan wall was kind of the ultimate part of that. Both of these data centers have extremely large, deep floors. Um, uh, NCAR's is 8 foot tall, and I'll have a picture of that coming up. The ESIF facility, because it sits on that South Table Mountain and there's such a grade change, we actually have 18 feet under the data center raised floor. And we actually put mechanical gear directly under to shorten piping runs and copper distances and that kind of thing. So um, both take the philosophy of taking things very low in your fan curve. You can move lots of water very slowly, or you can move it very quickly. Same thing with air. More efficient to move large volumes very slowly than it is to move it at high velocity. And I would say one of the other novel things that we did at NWC, because water is a real constraining resource, in the current environment where we haven't had enough moisture, they may actually put us on restrictions and we would pay a lot more than what was originally planned. But for that facility, we went to a zero blowdown technology. So we soften the water, we add silica, and basically on the internal sections of the pipe, it basically produces a very thin coating of sedimentary rock inside the piping, and it stops all your corrosion. Um, so with zero blowdown, it also means that we can drive our pH high, and so the water at NWSC is, I think, like uh, pH of like 9.5, and it greatly reduces the amount of biological biocides and things you have to use, so you don't have to replenish your water. There's also a massive filtration system because a lot of the dissolved solids actually precipitate out, and you get magnesium and salts and all kinds of things that we filter out. But it saves about 6 million gallons a year, so it was considerable water savings. Both facilities use heat reuse. I'll feature a little more of that in the ESIF facility because we were more advanced on the later facility. So these are examples of the evaporative cooling towers. Again, everything's oversized. That's 32-inch pipe. I'm large enough I can't quite crawl through it, but if you're skinnier, those are substantial pipes, and then plate and frame heat exchangers. We also drove the architects crazy because we said we wanted 45-degree angles for piping. So that's not a tilted picture. It really is 45 degrees, and that eliminates a lot of drag in the piping. 90-degree elbows create this turbulent and drag. So everywhere we could, we put in 45-degree piping locations. This is that fan wall I mentioned. So this is 150 feet long. Each one of those filters behind it is a fan that's drawing through that filter. And then there's a fan coil in there that provides the cooling. It's honestly, if you're standing in front of it, you can have a conversation. It's moving very, very slow. The actual fans are operating at like 5-6% most of the time. And
So Aaron,
yeah.
oh, sorry, wrong Aaron. Yeah, sorry. We have an Aaron in the room and we have a bit of confusion for just a moment. But I was going to ask, with the fans operating at normal levels, about how much CFM are you looking at?
I think It's been a while since I've thought about that number, but I think we're somewhere between 150 and 200,000 cubic feet a minute.
Ooh-wee.
So with, with doing the wide not fast, do you wind up with fronts in the room?
I'm sorry, what's the question again?
With going for the wide not fast, do you wind up with like notable fronts in the full space?
Um, no, during commissioning, I would say one of the interesting things, we really had to get our raised floor balance correct. So you have to have the right number of perf tiles, um, to match that, let's just say 200,000 cubic feet a minute. Um, we could levitate tiles, which was kind of cool.
Okay, this is.
Kind of frightening, but there was enough pressure that, yeah, we could levitate tiles if we had too much of the floor closed down.
Holy cow. Is it safe to be down there?
This is
Uh,
safe places, my friend. Not for any part of it.
Safe. I don't have the right picture for that discussion, but the fans originally are open, like, the motor is actually inside, and then the actual fan blades are exterior. And we thought, oh, it's a secured space. Safety is fine with it. Our safety officer was fine with it. But the very first tour we took down there, it was a senior like NSF person, and they're like, I have the urge to want to try and touch those. And you're like,
No.
no, 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 do not. So we put fencing. It's um uh think of it as kind of like a fancy chicken wire fencing. So you can't actually reach in and touch fans without like shutting things down.
Fans are so shiny one out. Yeah. It's so shiny.
Yeah, shiny spinny things. So this is a ghosted image of the whole facility. It gives you kind of a whole picture. And one of the things about efficiency is we were able to strip down to just the absolute bare minimum components. So if you really think about the system, we're able to move, um, from the data center to the heat exchanger. There's three sets of pumps and two heat exchangers. So the internal water that's cooling the data center is completely clean, never sees outside conditions. We put corrosion inhibitors and the normal kinds of water treatment you would in a closed loop building. You got those multiple headers, and you can reach to any computer system on the floor that requires liquid cooling. Um, and so you're just circulating fluid through that loop, supply and return. The condenser side is the same, and we were very concerned at NCAR about thermal ride through, especially as you got to these really high densities. And systems will shut down in like sub-second, 2 seconds when they're overheating. Um, so that large storage tank is just a thermal battery. So it provides, we dump the heat to that location, and then we pick it up from the towers, and it just creates this buffer, which gave us something more like 35, 40 minutes to react instead of seconds. But that was 165,000 gallons of water in an insulated tank.
So for those of us who are just SSHing into these things, what is thermal ride?
So yeah, so thermal ride through is the amount of time you have between you from going, on most chips, if the chip temperature goes higher than 90 degrees C, so 100 and whatever that is, 145 F, most chips currently will first throttle themselves down and then will actually shut themselves off to keep from thermally damaging themselves.
Right, there's like a tolerance to that.
Yeah, so ride through just means we slow down how quickly you see the warmest part of the water because the tank will stratify. Hot hot fluid rises, cold is at the bottom. We draw out of the bottom and until the hot actually gets down to a level that we can no longer, maintain it, then the thermal storage works against us, but it keeps everything cool for like the amount of time that we want to gracefully shut down.
So when you say thermal ride through, you just mean making sure the water is cool enough it can actually cool all the systems. You're not carrying heat through to the systems.
Correct.
So like the
And
whole system's capacity to survive.
yep, exactly.
Water was in the whole system versus the reservoir.
The reservoir was about the 2x the capacity of all the piping. And that was purely a function of how much ride-through time we wanted. Um, we also played some games with the geometry, so that the tank is relatively tall and skinny, which gave us a lot more head pressure, which meant that if a pump would fail, gravity would still drive cold water to where we wanted it to go.
Did you ever actually do testing scenarios where you did these power failures or cooling failures, or is it all just simulated?
Um, so we actually experienced when I was there 2 cooling failures, and um, one of them we rode through with flying colors, and the second one we actually did not get as much time as we'd anticipated. Um, in both cases, we didn't cause any real damage, but um, we the first failure scenario was actually a control sequence that the valving failed. And so we shut a portion of the valving off, which caused the head pressure to go out of um,
Was this
design conditions, and so the pump shut off.
was this on purpose to test the system, or was this just an event?
I know it was a control sequence. Oops, when we were doing an upgrade. Typical, typical kind of thing, right? It went to a system default, and the system default was normally closed, and it should have been normally open.
The fun way to find the bugs in the system.
Yes, yeah. The second failure scenario was a planned outage, and um, we were going to try and ride through a heat exchanger maintenance window on one heat exchanger. And that's the scenario where we, calculations and modeling, we're like, oh, we got 2 hours. No, we only had about 35 minutes. So we did end up having to shut down that data center to complete that maintenance. Uh, Probably the mission critical load that we operated there. We did Antarctic forecasts for National Science Foundation. So anytime there's researchers at the South Pole Observatory, we're supposed to be able to get a 4-hour weather forecast out. And in that case, we did have a contingency, so we actually ran that in cloud for the 4 hours we needed. So, let's see.
One question, so we're talking a lot about efficiency in here. And at least from the simplified picture that you're showing on screen, it seems like in theory, you wouldn't have a lot of noise in the physical floor. What, at least comparatively to a normal data center, can you describe what the noise level would have or would be like on the physical floor itself, since everything is liquid cooled?
Yeah, and in both cases, the data centers are probably 60% quieter than a typical data center.
Not what I think.
And that's because all the server fans are stripped out. And again, we're moving everything slow. And so you don't get the auditory thermal or, from a fast moving fan. So they're notably quiet.
Thank you.
So jump forward a little bit, just some highlights, how well we did. The facility received 2 national level awards, and the facility was LEED Gold certified, and I'd say we demonstrated a power usage effectiveness of 108. So
What does that represent?
So for every megawatt into the facility, um, it would mean that you're using 8 kilowatts for cooling to cool the 1 megawatt.
Okay.
Is the way to think about it. Most data centers, traditional design, are like 1.4. So this was truly world class. But ESIF topped it. So I'll jump to that. So that's NCAR. This was the design philosophy for ESIF, which was just slightly behind, and actually a number of the engineering teams and myself on advisory kind of capacity. We did a couple things that were more innovative. We really pushed to bring warmer temperature water to the to the computing systems. Traditional design always said, "Oh, you got to have 50-degree F water," and we're looking at it going, people are happy up to about 75. We should push to there. And the chip is perfectly happy at 140. As a mechanical engineer, I'm like, there's a lot of room there. And so we drove to what we were calling warm water liquid cooling on the ESIF facility. They also paid a lot more attention to some of the electrical distribution systems in that era in the 2010 timeframe. 208 volt was very typical. These are now 480 volt. Our ESIF dictated to vendors that they wanted 480 volt AC direct to the rack and eliminated a bunch of transformation steps. And both facilities did take advantage of heat reuse, but ESIF does a better job of it because we can temper air to all those lab spaces. And so there's more of a customer in the ESIF building. So we can actually, uh, we we worked within the industry to form energy reuse effectiveness. And so at times, the ESIF facility can take 30% of its heat discharge and actually heat the building. So there you can go better than 1.0 because you're making use of the heat energy that you already had. And we've achieved PUEs at NLR of 1036. So that still is really world class, and not many places have demonstrated better. I don't know. You do hit points of diminishing returns. Much lower than that is certainly possible, but you spend an awful lot of money to get there for not a lot of benefit. So that's in both projects. I operated under kind of a rule of we had to see a 5-year return on investment if it was a technology purchase that cost us more from a energy perspective. So it had to pay back in 5 years in order for us to do it. So Um, this is ESIF, a little different view of it. The black box, pun intended, is the main data center. So that is 10 megawatts, 10,000 square feet. It's roughly half the size as far as data center goes of NCAR. That one is 20,000 square feet of raised floor and two modules, each capable of 10 megawatts. So 20 megawatts on that site, 10 for this one. And that used to feel like kind of a big, capable data center, but now everybody's talking about gigawatts, so it's kind of crazy. Mentioned heat reuse, and this is the underfloor that I mentioned where it's 18 feet. So we actually moved heat exchangers and pipe and pumping under the data center to shorten our spaces. That facility also did really well. They went for a platinum LEED certification and uh, received an R&D 100 award. That was in 2014. I didn't actually put that on the slide. And then a Data Center Dynamics award in 2018. So both are highly recognized facilities for what they're capable of. Jump to the last part, which is kind of some of the things I'm working on now. There's a ARPA-E program called COOLERCHIPS, and it's 15 projects. Our lab is the actual test and validation facility for those projects. So there's 11 innovative like cooling track projects that were awarded. So each were on the order of 3 million for, a 3-year project. And then there are 3 that were selected to do modular, like full component build out. And they all have to show considerable improvement over energy efficiency. And one of the main things we're focused on here is managing the thermal resistance at the chip level. If you can manage the thermal resistance more effectively, you can start to approach those much higher temperatures. And projects here have to demonstrate that they can accept supply temperatures to the chip on the order of 50 degrees C, so 110, 120. And well under that 145, 90 C number that I talk about. So you're no longer warm water cooling at that level, you're hot water cooling. But what that allows us to do is we can eliminate entirely the evaporative cycle, and you can meet those kind of temperatures even in, Phoenix, Arizona, or Miami, Florida, without a chiller. So this would drive the kind of like approaches that we did for the 2 facilities, but you could do that anywhere in the continental US.
So how
So
long
that-
before we have SMR powered data centers? Isn't that where the research is going right now? SMR? Small modular.
Small modular reactors, that is absolutely the push on the power side. I mean, I think there's well understood that we've not added capacity to the US electrical grid for almost 40 years. And now there's huge uptick in generation needed, transmission needed, etc., mostly to support AI. And so yeah, there's a big push on SMRs. I think there's also just a big push on whatever power we can get as fast as we can get it. Realistically, I still think permitting for SMRs is going to be lengthy. And there are technical challenges with SMRs because they're really great for baseload. But I've got colleagues at Idaho that are certainly more versed in the power generation side from nuclear than I am. But in several of their talks, they have to marry that with either natural gas generators or renewables or batteries because the ramp rate for SMRs is too slow. It's in the order of, seconds. And with AI workloads, we're seeing microsecond jumps. Um, if you're at a gigawatt, those microsecond jumps can be 10 megawatts of load up and down, which the grid doesn't like, the Mars don't like. So there's a lot of work on the bridge also. So super caps at the kind of like at the rack level, and batteries, like battery, best style, like utility scale batteries to dampen kind of like shock absorbers in the electrical grid. So
Do SMRs contribute to grid inertia? Or most of them direct?
My immediate reaction is yes, because most of them are rotational turbine.
Are any of them even tied into the grid? I think they're
Like
all isolated.
The grid inertia happens to small scale too.
Yeah. I defer to some of you all if the early ones that I'm aware of are islanded.
Okay, or what?
Are islanded, so they're not tied to the grid resource. They're like they have a dedicated customer and they use all the power that SMR puts out.
Aaron, I've read a little bit about the possibility of using data center waste heat for like urban heating. Do you think that's actually realistic?
Um, Distances kill you.
It's free heat, but
It's getting there.
yep.
It's free heat, but it's pretty low grade. Where they've done it successfully in Europe, um, I've got colleagues at the Swiss Supercomputing Center, and that data center is right smack in the middle of a residential area. And they basically reject their waste heat to the city thermal system, and it kind of trims, same idea. So that's cost effective, but it's because of where it sits. Other one that's really makes good use of that is the Lumi facility in Finland, and they're above the Arctic Circle, so there's always demand for heat, almost always. Um, and they boost it. So they take their waste heat off the data center and then they boost it with heat pumps. And that looks very promising, especially if your heat pump is efficient. So it's viable. Devil's in the details. Um, and like if you got to go lots of piping distance, you both lose, a certain amount of degrees as it is moving. And it's just the cost of that much piping.
What about
This-
geothermal at data centers? Is that getting traction or that's still too much?
Definitely being looked at, especially in locations where geothermal makes sense.
So location dependent, honestly.
I think another really interesting project that is using ground source as more like your thermal reservoir, and so you pre-cool at night, and basically make the ground colder.
For the daytime?
It's a reverse.
And then you ride through on the daytime, so it reduces your water use. It also lets you load shift. So if you've got capacity demand charges from like noon to 4 o'clock in the afternoon or 6 o'clock in the evening or whatever your demand charges where electricity goes more expensive, you can shift your demand charge to nighttime. And those are some kind of interesting discussions.
There's actually a skyscraper in New York City that they use demand charges and literally make ice at night and use the ice to cool during the day. So it's a similar concept. Makes sense.
exactly same idea. Is it's just thermal storage, and they're using geothermal because you can cool it and it stays cool long enough, and you can shift your peak demand out.
If you think about it, we have to do leveling over the power region all the way down into. I made the joke about bypass capacitor earlier today. It's just the thing,
So,
but at every level.
so you ask about heat reuse. I'll throw this out there just for discussion because it's one of my crazy ideas, and I don't know if it's viable or not. But you're the right kind of crowd to ask about it. So if you had a very capable GPU system that was your like home uh, entertainment AI, resource, and you could also monetize it. So like if you're not using the cycles on it, but you're willing to let somebody else use the cycles on it, um, you're almost at the right scale for, 1,200, 2,000 square foot home. That be your primary heat source would actually be
Like,
I think
back in the
I do that
2080s,
every winter when I turn on 3 more servers.
That's what I thought. I think I'm talking to the right audience.
mining rig that was yoked to a thermostat.
Yeah, that
Like back in the 2010s. The downside of it is the coefficient of performance of a resistive load is about 1.
Yeah.
And the coefficient of performance of a good heat pump is
Like
3,
above
5, more than 1.
But I do make 250 gallons of propane last 4 years, so it must help.
Yeah.
Yeah.
Well, like in
Yeah.
the US and where we are, I don't know if it's true where you are, it is. Direct resistive heat is not cost effective here. I don't know if it's cost effective where you are, but most people either run heat pumps or gas. You almost never see a true electric furnace in this area.
Yeah, and I think this sort of got proved out when people were trying to figure out justifications for buying Bitcoin at home. Where it was, hey, we can use this to heat our house, and it was like, yeah, think again. Now, the metrics may have changed, but it just doesn't seem, it seems like the technology or the flight of fantasy is sort of high on that.
Yeah, and it's very much like that same like crypto argument, but why I bring it up and why I mention it is I've seen a lot of things around cost of tokens, and I think it only makes sense with like AI inference.
The thing that gets you on inference is that there is effectively a setup time. And for something that fits in like a desk or can fit on a 15 amp circuit, the amount of stuff you're gonna have to spend to, we'll say, set up compared to how much runtime you have to cycle off again.
Yeah, I've been thinking about that too. So it's kind of like
Having me
They-
more test.
data gravity gets you every time.
I haven't gotten touch.
A peer-to-peer network for sharing inference load would be a real idea.
It would be, it would have to like block it, you have to really block it up based on specific models, because that load times.
Yeah, I mean, there's a lot of challenges there.
We've got an appliance that is basically, token pneumatic ridiculousness, and it takes half an hour to load a model. It produces stupidly fast tokens after that, but it takes half an hour to load the model.
Well, the bigger problem with any of it is to be useful is you need context. Context, that's what you lose. I mean, as soon as you load a repo and you load your context.
Well, so the fun thing is each time you do a cycle, you load in full context unless you cache it. And so if you're working with many, many customers, you're unlikely to be able to use that anyway. And so each time you chunk the machine, you are inputting a context and getting out that context plus. And there's no like strong relationship between this came out of this cycle. It doesn't have to go back into the next cycle. You need to doctor the context a little. But sorry, I nerd sniped badly.
Yep. Well, and this is actually my last slide, so these are just kind of wrapping up on like the way we've viewed things and kind of like my view of or opinions of lessons learned. Design with nature, not against it. She always wins. Uh, think beyond PUE. Simple metrics are great, but they're kind of just great for marketing. If you can go deeper than that and really measure the full picture, that would be what I would advise. Collaboration is huge. I think the lesson learned for me is I've learned from every engagement with every architect, engineer, operators. Had a really great discussion when uh, OLCF was just an idea, and some of the things that Oak Ridge were coming out, and Buddy Bland and I sat down, and I was like, "What would you do different?" And he was hugely forthcoming, which was helpful in our project. I kind of passed it on to the ESIF team. They've advanced it, and so that collaboration is huge. Um, I don't think this crowd would have issue with challenging assumptions, but the best ideas come out of challenging like the status quo or the kind of conventional wisdom. Test it, build it, measure it. So, if you can't measure it, it's really hard to optimize it. So, anyway, all things you all know, things you've probably heard, but those are things that I wanted to point out. And with that, thank you. So I also filled quite a lot of the time, but certainly happy to take questions.
One more question for you. If you had advice on getting into this career field as a focus, what would be your advice?
Oh, I would say be be constantly curious, and I would say one of the special things that I lucked into, but I'm able to translate between kind of the IT, this is what the applications and um, I've seen some disasters of projects where the mechanical electrical engineers are brilliant, the IT folks are brilliant, but they cannot talk to each other um, about requirements, or they just don't get each other. And um, I remember the first time I told a design engineer, I was like, no, we need to plan for 45 kilowatts in a rack. And they're like, we have never seen anybody go beyond 15. And we're like, well, we will.
It's almost my entire
And
house.
and we hit 250 and we can still manage it in the existing facility. I think we did it right. But yeah, I would say that curiosity, and I've been successful because I can translate like requirements and understand what a mechanical engineer is saying. So I think you got to have a little bit of both. Far too often, facilities like the IT folks don't talk to the facilities folks, and they don't speak the same language. So you got to figure out how to bridge that.
Yeah, they're usually silos pretty far apart, that's why.
Yep. This is where Ben says something about getting drinks.
Aaron, I'll say very interesting, and I really love the insights that you presented. One thing that I didn't expect from it was the natural environment cooling that you had from just the geography that you were in. So seeing that was really interesting to me.
Cool. Yeah, we're at altitude and we're dry, so it benefits us.
Just evaporating into like a free atmosphere, or are you doing some type of like recondensing setup?
Was that the question of just direct atmosphere?
So yeah, are you just evaporating the atmosphere, or is there some type of collection going on?
No, it's just direct atmosphere.
To just open loop and let it go?
And we benefit because of, we're at the Wyoming facility is at 6,200 feet, and The ESIF facility is like 5,400 feet. So we're at enough altitude that pressure actually benefits us. Our evaporation is easier. And we can't boil water. It's at a colder temperature.
Kind of surprised that that's cost effective. I guess water's just not that expensive.
Water's ridiculously cheap, and it's probably not fairly valued if I had to take my total opinion on it. I mean, for how precious it actually is versus what we actually pay for it is kind of shocking, the economics of it.
I guess now you also getting into shenanigans where the more, well, you're probably, I should finish the question. Where a certain river's flow was estimated very poorly when the water rates were so far ahead.
Wind overproduction, just a video on that river.
Wait, you did?
Yeah,
Oh,
it was like a week and a half, 2 weeks ago, when it gets down to the things. And
they
it's,
still have a giant, like,
Anyway,
backlog.
anyways, yeah. Are there any other questions? Tonight?
All right. Well, thanks, everybody.
Thank you.
Thank you, Aaron.
Good night.
Thank you very much.
Oh,
Does somebody have a drink on my behalf?
Let's kill this off.